All right, so I think we can get started. Good morning, everyone. So welcome to another seminar of the One World Signal Processing Seminar Series. My name is Miguel Rodriguez, and I'll be sharing this session this morning. And it is my immense pleasure to introduce you to Osvaldo Simeone. Osvaldo is a full professor at King's College London. He has contributed immensely to various fields, information theory, communication, signal processing, machine learning. He's a fellow of the IEEE, and today he will talk about the channel-driven Monte Carlo sampling, efficient distributed Bayesian learning in wireless systems. I'll ask everyone in the audience to, if you have questions, to post these questions on chat. And then towards the end of the session, we will address these questions. And without further ado, I'll leave you with Osvaldo.
Many thanks, Miguel and Marius, for the invitation, for the introduction. It's an honor to be speaking at this great series of seminars. I should mention at the beginning that we seem to be having some fire alarm issues. So if you hear some strange sounds, I might have to pause for a few minutes. Okay, having said that, my talk today is on the subject of distributed learning in wireless systems. It's possibly the most popular subject in the literature on wireless systems of the last few years. But unlike the literature that at least I am familiar with, I'll be taking a different approach. Instead of formulating the problem in a standard frequentist framework, I'll instead take a Bayesian approach, and I'll try to investigate what the implications of this choice, of this design choice are. This is work with Dongju Liu, who is a postdoc, currently a postdoc in my group at King's College London. Okay, so as I said, I'm going to discuss distributed learning, and this can be instantiated in two different types of settings. The first is the so-called wireless data center setting, in which a server has large amount of data, and this data is partitioned and allocated by the server to agents, to distributed agents, with the purpose of speeding up computation through parallelism. The type of protocol, and in this being a wireless data center, the agents are connected to the server using a wireless channel to avoid wiring and all the complications that arise from deploying the wired systems. The type of protocols that are implemented in this type of architecture are typically of one-shot, or embarrassingly parallel nature, which means that the agents will compute, typically do some kind of optimization to train a machine learning model, communicate only once to the server, and then the server will obtain the a global machine learning model, a global predictor, typically. The second setting is the maybe more popular now, federated learning setting, or parameter server setting more precisely, where data originates at the agents. So the server does not have any data of its own. And the data at the agent may even have privacy constraints. So the data sets are local. There may be privacy issues related to the sharing of information from agents to server. And typically the protocols that are implemented in this type of setting are of iterative nature. I think most of you may be familiar with the standard federated learning protocol. So I'll proceed as follows. First, I'll try to motivate why thinking about Bayesian learning instead of frequentist learning, and specifically why do so in a distributed setting. And then I'll briefly talk about the system model, which is extremely simple. And finally, I'll go over two different instantiations of, again, the idea of distributed learning, Bayesian learning in wireless systems, one for the data center setting and one for the federated learning setting. Okay, so let me start by motivating why we are concerned with Bayesian distributed learning. So underlying federated learning, deep learning, is the frequentist framework, the frequentist formulation of the learning problem, in which given a model class, say the class of neural networks, certain class of neural networks parameterized by some model parameters theta. The goal of learning, the goal of frequentist learning, is identifying a single vector of model parameters theta, which in some way is optimal given the data that is available at the learner or at the learners. So at the end of a frequentist learning protocol, distributed or centralized, the learner or the learners obtain a single value of the model parameter vector theta, let's call it theta star, and this theta star is used to make predictions. The Bayesian learning approach is some way broader in that the goal of learning is not that I have identifying a single model parameter vector theta, so again, the weights of a neural network, but rather that of optimizing over a distribution in the model parameter space, which I call Q here. And so this distribution assigns a value, a score, if you will, to every possible model parameter vector. So to every possible predictor that is in the class that you have selected. So in the class of neural networks, for instance, that you have selected. And so this distribution quantifies how compatible every possible model, every possible value of theta is, given the information that is available at the learner or at the learners. And we'll discuss this later in more detail, but clearly this type of distribution provides much more information than having a single value of theta. For one, it characterizes the uncertainty that there still is about the most useful model theta to use, given again, the evidence that is available at the learner or the learners. Now, ideally, this distribution Q should be computed by evaluating the posterior distribution P of theta, given all the data that is available at the agent or at the agents. Right? So ideally, we would want to compute the posterior distribution. And of course, computing the posterior distribution requires us to use Bayes' theorem. And so in order for all of us to be on the same page, I'm just going to use one slide to remind ourselves what Bayes' theorem says. And this is basically just, again, to review the fact that Bayes' theorem tells us that we should use the product rule to compute the posterior distribution. Okay, so the starting point of the Bayesian learning is our two distributions, right? Or rather a prior distribution, P of theta, in the model parameter space. And so this is much maligned, but really the prior distribution provides us with a flexible way to encode any information we may have about the most suitable models in the class we have selected for the particular problem. And so this typically requires domain knowledge. It also can be selected due to computational complexity constraints. Anyway, we start by choosing a prior distribution and also by selecting a likelihood. The likelihood is simply a forward model that describes, given any model parameter theta, the probability density on the possible observations. And so everybody's, I think, is familiar with the likelihood because this is exactly implemented by that neural network model class that I mentioned before. For instance, this P, this distribution on the observation may be a neural network with model parameters theta and a softmax output, for those of you who are familiar with that, which gives us a probability distribution on all possible outputs. So the starting point, the input to the Bayesian learning is the selection of a prior and the selection of a likelihood. And note that this is not unlike frequentist learning in that in frequentist learning, you also select a likelihood, right, which defines a loss function and a model, and also define a regularization function, which is related to this prior. Now, to illustrate what I just said, let's consider this simple setting where the model parameter is scalar, so it's a number, and the observation is also scalar, which is here on the vertical axis. Now, the input to the Bayes' theorem is again a prior distribution in the model parameter space, this dashed line, which again reflects our prior expectations on the best model parameters theta for the given problem, and a likelihood. Now, this likelihood is a bit more difficult to illustrate because for every different theta, it gives us a distribution on the observations. So what I plotted here are Gaussians, slices of Gaussian seen from above. So these are contour lines. And for instance, for theta equal to 2, What this tells us is that the likelihood says that the observations that are most likely are in this range. Again, this is a Gaussian seen from above. The mode is here in the middle. Okay, so the starting point is, again, we have this prior, we have this likelihood, which is a distribution for every given value of theta. Then we make an observation, we observe some data, let's say we observe 4. And now what Bayes' theorem tells us is that we should update our prior to a posterior. And the way to do that is simply to multiply the prior by the likelihood corresponding to the observation. So this function here with d fixed to the observation. And so this gives us another distribution, which is given by this product rule. And of course, to obtain a distribution, we also need to normalize this product. And this is the source of computational complexity, because normalizing requires integrating over all possible values of theta. But conceptually, this is very simple. You multiply your prior knowledge by the likelihood related to your observation, and you get a posterior distribution. And again, this posterior distribution is that function q that I've shown in the previous slide. So again, in frequentist learning, all that we would do is just to find one value of theta as the outcome of your learning process. So why would we want to go through the trouble of computing this posterior, which is a whole distribution, instead of just finding one value? There are several reasons for that. So let me just review some of them. First reason is, as it should probably be clear, is that Bayesian learning allows us to quantify uncertainty, particularly epistemic uncertainty. That is, uncertainty related to the fact that we may not have enough data to pin down an optimal value of theta, okay, in some sense, or the population optimal value of theta, if you know what I mean. To understand this is very easy. Consider this particular regression problem in which we only have data in this interval of values of the input, and there is no data here. So there is epistemic uncertainty here because we have, again, no data in this part of the plane. If you use Bayesian learning, what will happen is that that distribution Q, or the posterior ideally, will assign almost equal value of that distribution to all models that fit the data almost equally well in this part where we have data, and then we'll most likely disagree here where we don't have data, right? And so that disagreement quantifies the fact that we have uncertainty, and having, of course, information about uncertainty can be very useful in many sensitive applications, such as healthcare, and can also be useful for active learning, in which, knowing that there is uncertainty in these particular areas of the input space, one can then actively select inputs in these parts of the input space in order to reduce uncertainty. Another good reason to use Bayesian learning is that it is automatically robust to overfitting, and it even enables model selection without validation. And the reason is that if you choose a larger model class, unlike frequentist learning, the prior will need to be spread out over a larger space. And so models that tend to overfit will be down-weighted by the posterior distribution. And so this inherently gives some robustness to overfitting. The third reason, which gets us very close to the distributed learning setting that I'm interested in here, is the fact that Bayesian learning gives us a principled way to combine information from multiple sources, to combine data from multiple sources. And the reason, again, is that Bayesian learning applies the product rule. And so every time we observe new data from a different source, say, all that we need to do is to multiply the current posterior by the likelihood corresponding to that data, and then renormalize. Right? And this is, again, a principled way to account for information from multiple sources. And so this clearly takes us to the distributed learning setting that I'm interested in here in this talk. And to illustrate what I mean, let's just consider a simple toy example with two agents. So we have two agents, each one has its own data. Now the first agent can compute based on its own data, its local posterior distribution, which indicates how compatible different models are based on the information that that agent has, prior and likelihood, prior and data. And the same goes for the second agent. It can compute its own posterior. Now, should we use a frequentist approach, what each agent would do is just to summarize this entire distribution into one point, which corresponds to the maximum of these posterior distributions. And typically what happens in frequentist learning is that these point estimates are shared with the server. And then what the server does is just typically to average these two estimates, these two model parameters, which in this case gives us this point here. And this point here is clearly not good at all for any of the two agents, right? Because both agents give zero posterior distribution to both, to this point, which means that this value of theta is not compatible, is not useful in any way for neither of the agents. Now, of course, if we were to use Bayesian learning, this problem would be solved because all that we would do is to multiply, in principle, we would multiply these two posterior together and more precisely subposteriors, and we would get a global posterior that looks like this, which clearly indicates that there are two kind of main, two parts of the space that are useful for both of the agents in this particular way. Okay, so Bayesian learning gives us a principled way to combine information from multiple sources, in particular here from multiple agents, and it can therefore be more useful also from a theoretical perspective as compared to frequentist learning. There are, of course, problems, and so the question is, why shouldn't we do it? And the two main reasons why we wouldn't want to do it are, one, computational complexity. I've already mentioned that computing this posterior is computationally intensive, and so computing the exact posterior may just be out of reach. The second reason is the communication complexity, which, as you saw from the previous chart, arises from the fact that the agents would need to communicate to the server information about their, if you want to call it this way, the epistemic uncertainty, so the distribution in the model parameter space that they currently have based on their own data. So communicating that function is clearly much more intensive than communicating a single point, a single model parameter. So in this talk, we would like to make some steps towards arguing that both problems can be managed. In particular, to manage the computational complexity, and this is definitely not a new idea, it's a standard approach that has been popular since the 80s at least. We will rely on Monte Carlo sampling. I'll explain what I mean by in a second. And to deal with the communication complexity, I'll argue, and this is new, I believe, to this talk, that Monte Carlo sampling has an interesting synergy with communicating over noisy wireless channels. And in particular, what Monte Carlo sampling allows us to do is to repurpose channel noise for sampling that is a core subroutine of Monte Carlo sampling. So basically, noise in this way becomes a useful element or potentially useful element in developing distributed Bayesian learning solutions. So let me try to explain what I mean by this key idea, because this is really the key, the key point, and the rest are instantiations or illustrations of this general idea. So first off, what is Monte Carlo sampling? So as I said, ideally, in Bayesian learning, the learner or the learners will obtain a distribution in the model parameter space. Again, ideally, it should be the posterior distribution given the entire data set across all agents. Now, in practice, this is not feasible. And so what Monte Carlo sampling does is to represent and compute on these distributions, and so represent this distribution and compute over them through samples from this distribution. So we can represent a distribution through samples from such distribution, let's say S samples. So you can imagine that having information about these samples while not giving you full information about this distribution does allow you to estimate the distribution, for instance, using histogram or a kernel density estimate. It's also interesting to note that by choosing S, we get a handle on both computation complexity and communication complexity. So as we increase S, more samples, we get a better representation of this distribution. But of course, we also increase the complexity of communicating this distribution and processing, updating this distribution. Now, in practice, what do we do when we have multiple samples. So imagine you have done Bayesian learning, and as a result of using Monte Carlo sampling for this purpose, you have a number of samples, say 10 samples, S equal to 10 from this distribution. What do you do with these 10 samples as samples? Well, each one of these samples corresponds to a different predictor in a typical application of machine learning. So what you can do now is that you can take these S predictors and average the predictions obtained from each one of these predictors, right? So you can define an ensemble predictor in which you average the predictions of these S predictors. And what this does is exactly quantify uncertainty in the way that I explained earlier, quantifying epistemic uncertainty, because this ensemble accounts for the disagreement among different predictors. Now, okay, so this is Monte Carlo sampling. Now, what I'd like to argue is that Monte Carlo sampling, in particular, the idea that these distributions that agents have to communicate to the server are represented by samples, is very much aligned or is kind of synergistic with communication on noisy channels. So to explain this point, let me take a step back and just review standard reliable digital communication, right? So Shannon style communication on wireless channels or noisy channels. So the idea there is that the transmitter wishes to send a specific digital message to a receiver. So let's say 1 bit, just to make it easy. And it wishes to do so despite the presence of aleatoric uncertainty on the channel. So despite noise on the channel. And so the way this is done, of course, is to ensure that the conditional distributions of the samples received at the receiver, the distribution condition on either one of these 2 bits at the receiver side, are sufficiently apart so that the receiver can tell which bit was actually chosen by the transmitter, which was actually encoded by the transmitter, right? So the goal is to ensure that these 2 distributions are as far apart as possible. And so what we are doing through coding, through cranking out the power, is to mitigate the noisiness of the channel, the aleatoric uncertainty of the channel. So noise is deleterious, is harmful. If you think instead about the problem we have now in distributed Bayesian learning, situation is quite different, in that what the transmitter wants is to communicate to the receiver its state of epistemic uncertainty. So it wishes to explain to the receiver, to the server, that distribution Q of theta, right? In particular, it wishes the receiver, if we use Monte Carlo sampling, to have samples from that distribution. The transmitter doesn't care about which samples, right? Only wishes the receiver to have some samples from that particular distribution which describes its state of epistemic uncertainty, right? That Q distribution, or the posterior ideally. So if you think about it this way, what the transmitter can do is to shape the distribution of its input in such a way that the distribution of the output, which accounts for the noisiness of the channel, right, which is affected by the noisiness of the channel, as depicted in this picture, is as close as possible to the distribution that represents the state of epistemic uncertainty of the transmitter. And again, the transmitter does not even need to know which sample are received at the receiver side. It just wishes for the distribution of the output to be sufficiently close to its own state of epistemic uncertainty. And so the idea here is that if we properly design the system, the noise in the channel can actually serve as seed randomness as part of the sampling process that enables the receiver to have the right distribution for its samples. So one way that I like to talk about this problem is that we are using aleatoric uncertainty in the channel to communicate epistemic uncertainty from the receiver, from the transmitter, the agent, to the server. Okay, so this is kind of the key idea, and I'll try to apply this concept to both of the problems that I mentioned before. And I'll do so by looking at the very simple system model. Again, we have these 2 settings, the wireless data center, the parameter server, or federated learning setting. And the models would be straightforward. We just assume fading Gaussian with Gaussian noise channels. And we'll be looking at both orthogonal multiple access, or OMA, where agents communicate over orthogonal resources, or NOMA, non-orthogonal multiple access, where the signals from multiple agents are superimposed on the channel. Throughout, we'll also assume analog transmission, which means that the agents, upon completing their computations, so producing some signal that needs to be shared with the server, we'll discuss what exactly these signals are shortly. These signals are directly encoded by essentially mapping them through a scalar, through multiplication by a scalar on the signals transmitted on the channel. So this is typically called analog transmission or uncoded transmission. And the reason for looking into uncoded transmission are several. The first reason that has been explored in many papers and maybe too many papers in the literature is the idea that through superposition in the NOMA, when NOMA is used, one can aggregate in natural fashion on air signals from multiple sources. And so this can be much more efficient than combining separately transmitted signals. The second idea is that even in an OMA case, even if the transmissions are orthogonal, the channel noise can be repurposed as a mechanism to ensure privacy. I'll discuss this more in the second part of the talk later. And the third reason, which is, I think, introduced by this talk, is that this noise in the OMA and NOMA case can be repurposed as randomness for Monte Carlo sampling. Okay, so let's start with the first setting, the wireless data center problem. And what I'll be describing is a summary of results that you can find in this paper. Okay, so in this setting, we have, again, a server with a large data set. This large data set is partitioned across multiple agents in order to speed up computation. And the goal is through a one-shot communication protocol, as I'll describe in a second, the goal is for the server to have access to a number S of samples, which are approximately distributed from the global posterior distribution, where the global posterior distribution is obtained ideally through the product rule, in which we take the product of prior and the likelihoods for the data at each agent. Okay, so we want to do Monte Carlo sampling in this distributed way so that the server has access to samples from these distributions. And again, we'll be looking at one-shot or embarrassingly parallel protocols, which are also known as consensus Monte Carlo in the literature. And the assumption, the working assumption that one makes in these protocols is that the data sets at each agent are sufficiently small so that each agent can do exact Monte Carlo sampling on its own data set. So each agent can generate samples from its own local posterior distribution, more precisely sub-posterior, in that we need to take the prior to the power of 1/k to avoid overcounting it. Anyway, the point is that each agent can sample model parameter vectors theta from its own local posterior. And the goal is for the system to communicate these samples to the server so that the server can then combine these samples to obtain samples from the global posterior distribution, not from the local posterior distribution. Now, there is a scheme that is the state-of-the-art standard approach to do this in the case in which the channels are noiseless. And this is a standard scheme in the machine learning literature, and it's called Gaussian consensus Monte Carlo. So Gaussian consensus Monte Carlo works as follows. Agents, again, generate a number of samples, S samples from their own local posteriors, similar to the figure that I've shown before, and then send these particles, these samples, to the server over noiseless channels. What the server does is to first compute empirical covariance matrices for each one of the agents. Okay, so just estimate the covariance for each one of the agents. From these covariances, you compute weight matrices in this particular way, okay? And then the idea is that to compute one sample from the global posterior, approximately drawn from the global posterior, we combine linearly with these matrices one sample from each agent, okay? So again, we do linear combination through these matrices. And why would we want to do this? The reason why we choose this particular weights is because this choice is asymptotically exact in the sense that if we let the number of samples at each agent go to infinity, in which case these posteriors become Gaussian, asymptotically Gaussian. And then if we let the number of samples that are sent also to infinity, so that these covariances are exactly estimated or consistently estimated, then this approach is exact. So it gives you exactly samples from the global posterior. Okay. This is not difficult to see because when everything is Gaussian, these linear combinations exactly give you the posterior, the global posterior distribution. Of course, in the non-asymptotic regime, this scheme is no longer exact, but again, it is used nevertheless, even in non-asymptotic regimes. So what we have done in this context is first, we have developed a wireless version of this Gaussian consensus Monte Carlo scheme. This is quite straightforward. But the interesting point here is that this asymptotically exactness will hold no matter what the level of signal to noise ratio is. So the point here will be that the noise will have no effect in the asymptotic regime of a large number of samples. Maybe this is not that surprising, but if you think about it, it might be because what this says is that even if, again, we have a very low SNR, this has no effect on the asymptotic exactness of the scheme. Then we tackled the problem in the non-asymptotic regime, in which we propose a new scheme that tries to optimize those matrices W, those combining matrices W, based on the samples that the server has received, as well as based on the data that the server has. Remember that the server has data, so you can access it through mini batching. So we'll propose a scheme through which the server can optimize those weights and perform better than this Gaussian consensus Monte Carlo scheme in the non-asymptotic regime. Okay, so as I said before, all schemes are based on analog transmission. So the each agent K will sample from its local posterior and will simply take this sample and encode it by simply multiplying by a scalar for communication on the channel. This scalar should satisfy the power constraint. And then the receiver side, so the server, will simply combine the noisy received signals with some matrices W, just like in the Gaussian consensus Monte Carlo scheme. But now we combine noisy received samples. And in the NOMA case, of course, we don't have access to separate signals from every agent, so we can just multiply the overall received signal by some matrix W. Now, the first scheme that we consider is, again, a wireless version of the Gaussian consensus Monte Carlo scheme, which is very similar to the consensus Monte Carlo scheme that I described before. The only difference is that in defining these weights, one needs to account for the fact that there is noise in the channel. But again, this is quite straightforward. And the key point here is the observation that no matter what the SNR is, this scheme will still be asymptotically exact. It will still give you the right samples. It's also useful to note that in the NOMA case, this is true for OMA. For the NOMA case, this asymptotic exactness only holds if the sub-posteriors are homogeneous. They are the same across all agents, which is a very limiting assumption. And this is due to the fact that we can only do essentially equal combining if we use NOMA. We cannot really control the way in which these samples are combined. Now, more interesting is the case where we would like to be to optimize the distribution of the samples aggregated at the server, even in the non-asymptotic regime. So ideally, what we would like is for the distribution of the samples aggregated at the server with some weights W to be as close as possible to the global posterior, right? So this is ideally what we would want. We would want these two distributions to be as close as possible. So we could try to minimize a measure of distance between these two distributions. And for instance, a classical choice is the KL, the Kullback-Leibler divergence. Now, of course, minimizing this metric over W is not feasible because clearly the server does not have access to the true global posterior. If it did, the problem would be over. So one needs to make some approximations and simplifications to this problem so that it can be actually tackled at the server based on samples received from the agents and its own data. It can also some mini batch access to its own data. So there are a couple of steps to these simplifications. The first is and this is standard step, instead of minimizing the KL divergence, to minimize the equivalent metric, which is free energy or ELVO, evidence lower bound. The second step is to bound the entropy using the entropy power inequality. Anyway, at the end of all this process, one gets a criterion that can be optimized using stochastic gradient descent. And so the overall picture is as shown in this figure. So the agents send their particles on these noisy channels. The server takes all these particles and solves an optimization problem over the weight matrices W. And to do so, it also uses a little bit of its own data to help it compute the quantities that are needed. And at the end of this process, it gets some optimized weights W, which are adapted to the given statistics of the samples, and combines the samples accordingly using that linear combination function. So let me show you how these schemes perform. And a standard way to evaluate the performance of the schemes is to compare the ensemble average that you get using the samples, the global samples computed at the server, with the true averages that you would get had you known the exact global posterior. Okay, so we want to measure how far we are from the from averages of some test function f with respect to the global posterior distribution. So we did a lot of experiments using both synthetic data and actual data. And I just would like to point to a couple of standard behaviors that we have observed in these results. So the first thing to observe is, we plot that test error versus the number of communication blocks, so versus the number of samples that the server is obtaining from the agents. So the first thing to observe is that the Gaussian consensus Monte Carlo scheme is asymptotically optimal as per theory, but it can be widely outperformed by the variational scheme, that optimization-based scheme that I proposed, the second scheme that I talked about. Also, in this particular setting, which the subposteriors are homogeneous, the NOMA can beat OMA, but that's not always the case. In particular, when there is heterogeneity, that's no longer generally the case. But more interesting is the performance that you get if you plot the error versus the SNR. So I think this is the most striking result that one can observe in this type of Bayesian distributed learning problems. So what this says is that if one optimizes those matrices, so if we use that variational optimization-based scheme, the second scheme, the performance is for a large range of SNRs independent of the level of noise. So the performance almost does not depend on the SNR at all. I've chosen here a particularly good setting where this happens for a large range, very large range of SNRs. This is, of course, not always the case, but it's always the case that there is robustness to the level of SNR for a large range of value of the SNR. And again, this is all due to the fact that what we are doing is leverage the noise in the channel as seed randomness. The last figure that I just want to quickly point to is shows that the number of computations that are needed at the server is much less, much smaller than the amount of computations that the server would need to do had it not used the agents. Right? So we still gain from the parallelism of the agent side. Okay, so in this first part, I've hopefully brought some evidence to the idea that the Monte Carlo sampling, Bayesian learning based on Monte Carlo sampling, can be efficiently implemented on noisy channels. And I have done so for these one-shot protocols in the wireless data center setting. What I'd like to do next, more briefly, is to talk about the second setting, so the more common federated learning setting, or parameter server problem. So here, as we said, agents have their own data. The server has no data of its own. The goal is still the same. We still want the server to obtain samples from the global posterior. But now we are allowed to use iterative protocols for this purpose. And because the data is local at each agent, we also have to account generally for privacy constraints. So the key new element here is really the presence of these privacy constraints and the fact that we're using these iterative protocols. So the standard approach to quantify privacy is differential privacy. Differential privacy depends on two parameters, epsilon and delta. The smaller you make them, the more private the scheme is. And what the differential privacy is meant to represent or to account for is a situation where the server is honest but curious. So the server is following the protocol, but may try to infer information about the data points at the agents. So in particular, the server may try to do membership inference or model reverse engineering attacks. So may try to figure out, based on information about the model, which data points were used to obtain that particular machine learning model. Now, we don't need to bother here with the specific definition of DP. What we need to know, however, is that DP can be guaranteed if the learner, before sharing its statistic, the output of its learning process, adds Gaussian noise. And the level of noise that needs to be added depends on how private we would like communication to be. And in particular, therefore, this level of noise will be increasing as we decrease epsilon and delta. Okay, that's really all that we need to know for the purpose of this talk. Now, again, we would like to implement iterative Markov chain sampling protocols, and a standard approach, possibly the simplest approach to do that, is Langevin Monte Carlo. So Langevin Monte Carlo is an efficient state-of-the-art Markov chain Monte Carlo scheme. Markov chain Monte Carlo are schemes that operate iteratively over time, unlike the consensus Monte Carlo schemes that I mentioned before. And LMC, Langevin Monte Carlo, is basically just a simple tweak on standard gradient descent learning for frequentist learning that I think you're all familiar with. So the way this works is as follows. Let's first define, as you would do in a standard frequentist formulation of the Bayesian learning problem, let's define the global objective function. So this has a sum of losses local for each agent, and then a regularizer term, which depends on the prior. Now, if you wanted to implement standard frequentist learning, what you would do is just take the gradient of this global loss function and follow it down, hopefully, to a stationary point of the global loss function. Now, LMC almost does the same thing, with the only difference that it adds to the gradient step, it adds Gaussian noise, again, Gaussian noise. And the key point, an important point, is that this Gaussian noise has a variance, which is twice the learning rate used by gradient descent. So you can think of LMC as gradient descent plus Gaussian noise with a particular variance. Why do we choose this particular variance? We choose it because this discrete time iterative scheme is a discretization of a continuous time diffusion process known as the Langevin diffusion process, which comes from statistical physics. And the key property of that process is that after a while, asymptotically, it is such that the samples produced by that process have exactly a distribution that equals the posterior distribution. Okay, so this is quite magic, but as time goes on, the distribution of these samples, the marginal distribution, will be exactly what we want, so the posterior distribution. Now, because of course we discretize, there will be a gap between the posterior and the distribution of the samples, but this gap can be quantified as a function of the learning rate and as a function of the distribution F, the global loss function. And so the way these schemes work, because of these asymptotic properties is that you'll run them for a number of iterations. You'll discard the first few samples known as the burning period, and then you'll obtain your ensemble predictor by using the last few samples. Okay, so how do we implement Langevin Monte Carlo in a federated learning setting? I think you can definitely guess it at this point. So we use standard federated gradient descent, and all that we need to do is to keep track of the fact that we have to add in some way that Gaussian noise, right, to the updates. And so the way it works is that the server at every iteration sends the current sample. Point here is to think of this theta not as the current iterate that we replace, but as the current sample that we will preserve to do the final estimate after the burning period. So the server broadcasts the current sample. The agents compute their gradients, send it back to the server on a wireless channel, and the server will use these noisy signals to estimate the LMC update. We use analog transmission, as I said. So we take the gradients and multiply them by some gain. And in this part of the talk, we'll actually be concerned with optimizing these gains. That's where the interesting theoretical part occurs. And the server then will take these, we are considering NOMA here, so we'll take these combined samples, this received signal Y, we'll scale it down, or scale it with some coefficient, and then possibly add noise. And the reason for possibly adding noise is that, remember, we want to implement LMC. So LMC requires additive noise, even if the channel is completely noiseless. Okay, and if you write this down explicitly, what you'll find is that all that we have done, all that the server is doing, is to apply an update that is much like LMC, but there may be additional noise caused by maybe an excessively low SNR that affects the gradient. Okay, so the point here is that we're using the noise in the channel partly as LMC noise, as noise that we anyway need to add to implement LMC. So what we have done at the technical level in this work is to ask whether we can optimize those gains alpha to ensure that the distribution of the samples becomes as close as possible to the true posterior, just like the criterion that I've described before. And so in this part of the talk, we were interested in optimizing those gains, alpha gains, to ensure that the distribution of the samples is as close as possible to the global posterior, while satisfying power constraint and privacy constraints. For Langevin Monte Carlo, it's typical to use the 2 Wasserstein distance, not the KL divergence. So that's what we did. And interestingly, we found that this problem can be solved in closed form if one uses suitable bounds on this distance. And the solution is actually quite neat, quite simple to explain. So in this figure, I show the SNR level and the learning rate. And remember, the goal here is to understand how to choose those power gains. So how much each device, each agent needs to back off from the maximum power so as to satisfy the SNR requirements of LMC and of privacy. Okay. So what this figure says is that there is a regime in which the devices do not need to back off at all. And then there are 2 regimes in which they need to back off to degrade the SNR, either to satisfy LMC constraints or privacy constraints. And the key point here is that in these 2 regimes, the performance is the same as that of a system that had no noise. So the reason is that even in a system where you had no noise, you would have to add noise to implement LMC or to be private. And so the point here is that in these 2 regimes, the SNR level is irrelevant. The level of noise is irrelevant because in the sense that you get the same performance you would get in a completely noiseless system. To illustrate this, again, we have done a number of simulations. Here is for a particular likelihood and a particular prior. And the key point that I want to stress here is the benchmarking we have done. We have benchmarked the system with that of a noiseless system. So the channel, there is no wireless channel anymore, a completely noiseless system. We want to compare our performance with the performance of such noiseless system, either with or without privacy. And the bottom line is illustrated by this figure, where I show the distance, the Wasserstein distance, the two Wasserstein distance between the distribution that we want, the global posterior, and the actual distribution we get as a function of the SNR. The two straight lines correspond to the performance of a noiseless system with privacy or without privacy constraints. Of course, the system with no noise is a benchmark and it's not affected by the SNR. The key observation is that in the system with noise, optimized using the method that I alluded to and we have proposed, the performance tends to the performance of this noiseless system as the SNR goes up, but this happens at a finite SNR. So the point is that at this level of SNR, the system behaves exactly the same as a noiseless system. And again, this is because we are using the noise that we have on the channel as seed randomness to implement LMC or to satisfy privacy constraints. And so the bottom line also of the second part concerning federated learning is that if we implement Bayesian learning in a distributed setting using Monte Carlo sampling, we can leverage the noise on the channel as seed randomness, in this case, to implement LMC-based, so Markov chain Monte Carlo updates. Now, these two papers that I presented are, of course, just initial steps in this type of research program, in which the idea is to try to implement Bayesian learning, which is seen a resurgence in machine learning, also in machine learning conference venues and machine learning research in wireless settings. And there are, of course, many open problems, I believe, in this field. So in the two problems that I described, there are, again, many directions that we have not explored. For instance, one in the first, for the data center setting, one could look at nonlinear aggregation functions, trying to optimize also the encoding. In the federated learning setting, one may try to also optimize the learning rate, which is non-trivial, or compare with quantization-based implementations, or look at D2D network topologies. Okay, so with that, I'd like to conclude, and I'll be very happy to take any questions from you. Thank you.
All right, so thank you so much, Osvaldo, for your talk. Yes, so any questions from anyone to Osvaldo? Yeah, so there's one question on the chat, and this is from Bezahi, who asks, can we use NOMA with hybrid beamforming, and how?
I don't know that I see the connection with what I discussed. So, I mean, I think the only thing I can say about this is that in this talk, we were only concerned with the receiver side processing, right? So we optimized those aggregation matrices in the first part of the talk, at least. In the second part, we just were after power allocation. So I guess in the first part, for the first part of the talk for consensus Monte Carlo, those aggregation matrices could be implemented using hybrid beamforming. That, of course, would pose additional constraints on the shape of those W matrices, right? You'd have to be the product of a digital component and an analog component. So yeah, I can imagine that you can try to optimize them using gradient descent, maybe on proper manifold. But yes, we haven't looked into that. But yeah, it's a meaningful. I think it would be a meaningful direction for research.
All right, very good. Thank you so much. Any other question for Osvaldo?
How
All right.
to deal with non-ID data in local agent. Okay, maybe you should read it, Miguel. Sorry.
Okay. So I can do that. So this question is how to deal with non-IID data in local agents with Bayesian learning.
Right. So, as maybe clear from the first example, like the toy example that I've given, at no point one makes any kind of assumption of homogeneity, right, of the posteriors, right? So in the Bayesian formulation, the goal is to obtain the global posterior. And so the idea that you want to account for every possible model for how much that model is compatible with the overall data set, right? So if each agent has, as in my first example, right? If each agent has heterogeneous distributions, then the global posterior will be multimodal. So that would be a kind of a sign that there may be incompatibility among different agents. And maybe that would be a sign that the model that has been assumed needs revising, right? So Bayesian learning is very flexible. So one could use a hierarchical model, right? Whereby now you assume that each agent has a local latent variable, and there is also a global variable. And so the goal here would be that the agents cooperate to obtain an approximation of the posterior at the level of the shared hyperparameter, right? But then each agent will try to evaluate its local posterior with respect to the local model, right? So what this will do is basically to assume that there is maybe one way to think about it. Maybe there is a set of models that are going to be good for all the agents, but the way in which these are combined, right, should be different for every agent, right? So the local distribution, the local latent variable here would be a variable that describes how these models should be combined. This is not the only way to implement these hierarchical models, but this is definitely one way. So I think the point here is that if you take a Bayesian approach, it's just a matter of choosing the right model. Once you choose the right model, or for instance, hierarchical, not hierarchical, then there is no additional assumption to be made, right? One is just following a principled approach to formulate a learning problem. And the key point, of course, is choosing the right model in which to formulate that problem. So all those issues of heterogeneous non-IID-ness can be handled in this in my opinion, much more natural and principled way.
All right, so thank you very much. Any other question for Osvaldo from anyone? Maybe I'll make a question. And so Osvaldo, coming back to your first setting, so you do compare, this initial Gaussian scheme with the variational one. And, of course, at finite SNR, they differ. The variational one is better than the other one. But my understanding from what you have presented is that at infinite SNR, as you increase the SNR, the original Gaussian scheme is optimal, right? And in that sense, why do they differ? Why is the variational better?
I guess I wasn't very clear there. So yeah, no, the asymptotic optimality of Gaussian consensus Monte Carlo is asymptotic with respect to the amount of data at each agent and the number of samples that are shared from agents to server. So that's the asymptotic regime I'm talking about. And the reason again is that if you have a lot of data at each agent, by the Bernstein-von Mises theorem, by the Bayesian central limit theorem, the posteriors become Gaussian asymptotically. And if you send a lot of samples, the server can compute the covariances of these distributions exactly. And so in that case, a linear combination is optimal. I mean, it gives you if everything is Gaussian, right? Of course, the product of Gaussians normalizes Gaussian. So that will give you samples from the true posterior, global posterior. So that's where exactness comes in. What I try to explain is that the wireless version of the scheme, in which we simply take into account that there is Gaussian noise, of course, adding Gaussian noise to a Gaussian variable just changes the variance or the covariance. So all we need to do is to account for that. And so what I said is that the asymptotic exactness, optimality, is preserved no matter what the SNR level is. Right?
Okay.
So it doesn't matter what the SNR is.
All right.
High, low, it's still always exactly optimal in that asymptotic regime. So the advantages of that scheme arise in the non-asymptotic regime, right, where you don't have a lot of data or not a lot of samples.
I see. All right. Thank you.
Yeah.
Any other question for Osvaldo? Okay, so there's one prompt.
Go ahead. Sorry.
Is there any performance comparison between Bayesian learning and conventional frequentist learning, showing the former is more powerful?
Right. So there are a lot of papers on this topic, because the first question is, what should you compare, right? What type of metric should be used, right? So I read somewhere that 80% of NeurIPS papers use just accuracy as the metric of comparison. So if you just compare the accuracy and you have a lot of computational resources to spend and you have huge models, and you have a lot of data, then clearly Bayesian learning isn't the way to go, right? Because if you have a lot of data, the posteriors will, concentrate to a single point, and there is no need to quantify uncertainty. So Bayesian learning isn't useful, right? So the regime in which it becomes interesting is when data is limited. For instance, I think federated learning is a very good example, because individual agents may not have so much data, right? And so the big data regime that is assumed by frequentist learning will not be there. So in that case, one is interested in accuracy, in quantification of uncertainty, and in other auxiliary criteria, such as the capacity for continual learning, the capacity for active learning, right? So in terms of these additional criteria, such as, for instance, the calibration error, or the capacity to improve for continual learning or active learning, yes, there are many studies which show the advantages of Bayesian learning. If one is only concerned with accuracy in large data regime, then that gain isn't there. But as I try to explain, this is not a surprise, right? It should be like that, right? Bayesian learning tends to frequentist learning, right? There's a lot of data is available. So I think the issue is, as usual, defining the right metrics and working in the right regimes. And if you look at the last editions of NeurIPS or other machine learning conferences, you'll see there are many papers on Bayesian learning that make the case for it, right? Authors like Khan or Andrew Wilson, Imtiaz Khan, and I suggest maybe you look at their papers, and there are several position papers that explain when Bayesian learning is useful.
All right, very good. So any other question? Okay, so there's one from Liu Paichi. So the size of neural network models is typically very large. The communication overhead will be largely increased if MC sampling is applied and multiple model samples are sent. So how much sample should be sampled in practice?
Yeah, that's a very good question. So of course, communication complexity is an issue, and if you want to choose more than one sample, send more than one sample, of course, the communication complexity increases proportionally. I don't have a final answer to this question, but we did some study. I think I pointed to that paper in the references. Is a paper with my former student, Rahif Kassab. And so there we showed that you need just a handful of samples in the experiments that we have studied. Not only that, but if you look at the overall, not the per iteration, but the overall communication load, that's vastly reduced using this type of Bayesian methods. So if you look at the overall number of model parameters that you need to send over the course of training to achieve some level of performance between Bayesian and frequentist, in our experiments, Bayesian was consistently better, right? And I think this is not surprising because, especially at the beginning of training, as in my simple example showed, if you reduce everything to one model parameter, so if each agent just communicates one model parameter, that provides a very misleading picture of the information that the agent has, right? So it takes much larger number of iterations to get out of that kind of initial misunderstanding. But if you use Bayesian learning from the beginning, then agents can communicate that state of uncertainty. And we have seen that this can vastly improve the overall communication load. Of course, not the per iteration load. But I also think here there are many interesting directions to study. For instance, one can use more samples at the beginning, fewer samples later. One can use differential type of compression strategies for these samples. Because noise is not a problem. So compression may not have that much of an impact on on this type of protocols. So all of these aspects I think are very interesting, and I cannot say that we have explored them in depth. So I would suggest them as directions for further study.
All right, very good. So I think we'll take one last question, and this one is from Vivian. So why analog transmission? It seems that there are many recent works that consider such a scheme. Is this practical for implementation?
So why? I think I had a slide on that. So in principle, why is for the three reasons that I mentioned. You can leverage superposition for efficient aggregation. That's called air comp. You can use noise as a masking mechanism for privacy. And as I tried to explain in this talk, you can use it to do Monte Carlo sampling efficiently. Now, if you ask about how to implement it in practice, I have not implemented it in practice using, for instance, software-defined radios, but I did see some studies that have done just that. So I would point you to those papers in which I think they use USRPs in software-defined radios to implement. And I think there is also some earlier work by MIT folks, and it seems to be working, but there are certainly challenges related to synchronization and things of this sort. But again, it seems possible to overcome them. Now, there are, of course, issues such as interference that may need further study, but in principle, this seems feasible.
Okay, very good. So I take this opportunity to thank Professor Simeone once again for the talk. It's been very inspiring. And I also thank everyone for attending this seminar by Osvaldo. Before we part, I've got a quick announcement, and next week, the seminar will take place on Tuesday, not on Wednesday, so same time, but on Tuesday, not on Wednesday. So please make sure that you note it down. All right, so other than this, so again, thank you so much, Osvaldo, for your seminar. And
thank you very much for having me.
Everyone.
Thank you very much for having me. Bye.
Okay, bye-bye.